In this video, we'll consider the force of friction in both the static and kinetic conditions. Like the normal force, static friction is one of those reactive forces that changes in the presence of the circumstances present. For an example of this, let's look at what happens when we lean against a large boulder. Nothing, right? Although the result appears trivial, what's happening from a Newtonian perspective isn't. To get a feel for this, let's consider how we would interpret Newton's laws here. We know we're pushing on the boulder because its force keeps us from falling over. This is Newton's third law. But if we're pushing the boulder, Newton's second law says it should accelerate. A large mass, so only a little acceleration, but some acceleration, which isn't happening. The only way this can occur is if our force is not the only force acting on the boulder. Now, if we stop leaning, and that force that balanced ours was still there, the boulder should accelerate toward us, but it doesn't. This is where that reactive nature comes in. If we stop pushing, so does the friction. Now, what if, instead of leaning, we try to push the boulder? It still doesn't move. The only way we can use Newton's laws to explain this is if that opposing friction gets stronger as we push, even if we push really hard. Again, this is what we refer to as a reactive force. But what if we get reinforcement? Well, there is a maximum value for this friction. If we exceed this limit, the boulder moves after all. Of course, not all rocks are created equally, and the maximum friction values are much the same. It turns out that lighter rocks can be moved with less force. In reality, this friction is determined in part by the normal force acting on the object. If we compare moving an empty couch with one full of our friends, we get a sense of this. And sliding the same couch down a hill is much easier than it is on level ground. Both of these conditions affect the normal force acting on the object without material change to the object. But it's not just the normal force at work. The types of surfaces trying to slide past each other also have an effect. This is why hockey or curling are best played on ice surfaces. Now, the mechanisms are varied and subtle, but generally smoother surfaces experience less friction. Oddly enough, though, making surfaces too smooth can actually increase friction. To see this, try sliding two panes of glass past each other. In general, the limit to the friction that prevents an object from sliding, or static friction, is determined with this formula. The limit of the force of static friction is the product of the normal force, both measured in newtons, and what we'll call the coefficient of static friction, a dimensionless scaling factor, mu sub s. Generally, this coefficient of friction is determined empirically after many experimental trials, and has a range of values. Now, in general, it's easier to keep an object moving than it is to get it moving. That is, it requires less force. This suggests that friction changes once an object is moving. We call this form of resistance to motion kinetic friction. While the details are complicated and beyond the scope of this course, a simplified view attributes this to a drop in the coefficient of friction in the case of moving objects, or kinetic friction, compared to the static case before the surfaces move with respect to each other. The form of the equation is the same, the only difference is the value of the friction coefficient. To differentiate this from static friction, we use the subscript k for both the coefficient and the force of friction. Now, before we work on problems involving friction, it's important to note that values for friction forces and coefficients are inferred from the known forces that are applied and the resulting motion or lack of motion. For example, we know we haven't exceeded the limit for static friction as long as our running shoes grip the floor and our feet don't slip as we walk or run. Here we want more friction. Kinetic friction can be inferred from the amount of heat a car engine produces as the mechanical parts move past each other. This is where friction is less desirable, and we use lubricants to reduce the frictional coefficients. Now, if we take that couch full of friends with a total mass of 306 kilograms and start pushing, we find that it starts to move when our pushing force is 1,080 newtons. We can determine the coefficient of static friction by rearranging the friction formula, remembering that on a horizontal surface, the normal force is equal and opposite to the weight. Plugging in our values, we find that the static friction coefficient is 0.36. And if it now takes a force of 810 newtons to keep the couch moving with uniform velocity, applying Newton's second law, we determine that the net force is zero due to zero acceleration. Since this means friction and our push are equal in magnitude, we can perform a similar calculation to determine the kinetic friction coefficient. In this case, the coefficient is 0.27. Well, that's friction in a nutshell. The calculations are pretty simple, but applying them correctly is often a challenge. Don't be surprised if the subtleties of friction are confusing. Lots of practice will help you make the proper connections. When in doubt, ask questions, either online or in class. Good luck.